On your first trip to Planet X, you happen to take along a 200-gram mass, a 40-centimeter-long spring, a meter stick, and a stopwatch. You're curious about the freefall acceleration on Planet X, where ordinary tasks seem easier than on Earth, but you can't find this information in your visitor's guide. One night, you suspend the spring from the ceiling in your room and hang the mass from it. You find that the spring stretches by 31.2 centimeters. You then pull the mass down 10 centimeters and release it. With the stopwatch, you find that 10 oscillations take 14.5 seconds. Based on this information, what is G? So let's write down this information. This says that mass is equal to 200 grams, and the spring is 40 centimeters long, and that when you add the mass, the spring stretches by 31.2 centimeters, so the displacement is 31.2 centimeters, and when you pull the mass, the spring stretches another 10 centimeters, and we also know that 10 oscillations is equal to 14.5 seconds. Okay, so what does this tell us? So if you have 10 oscillations that happen in 14.5 seconds, let's say that this is 10 oscillations, then in order to find what one oscillation is from that point to that point, then you can divide 14.5 by 10 to find how long it takes for one oscillation. So we're going to get 1.45 seconds, and that is equal to the period. So if we have a spring and it's 40 centimeters long, that means that from its equilibrium position, it's going to be 40 centimeters long. When we add a mass to the spring, it stretches by some other amount, and we said that that mass was 200 grams, which is 0.2 kilograms. And that when we add the mass, it stretches an additional 31.2 centimeters. And then the problem says that we choose to stretch the spring another 10 centimeters. So what is G? Because the spring is hanging from the ceiling, we know that the force that is being applied on the spring that is pushing it down is M times G. There is going to be a restoring force from the spring going upwards. This restoring force is equal and opposite to the applied force that's pushing it down. And because it's hanging from the ceiling, we said that the applied force is going to be equal to mass times gravity, and from Hooke's law, the restoring force is going to be equal to negative k times x. If the spring is vertical, I'm going to change it to mg is equal to negative k times change in y. You might be wondering, what about the extra 10 centimeters that you push the spring down? Well, we're not going to care about that. This is because we want to find gravity, so we're only concerned with the force that gravity exerts on the spring. We don't care about how much we stretch the spring, we just care about how much it stretches from the force of gravity. We're ultimately trying to find G. Here we have mass and change in y, but we do not have k. But we do have the period. But we do know that the angular velocity omega is equal to 2 pi over t, and that omega is also equal to the square root of k divided by m. So we know that omega is equal to 2 pi divided by the period, which is 1.45 seconds, and that is equal to 4.33 radians per second. And omega is also equal to the square root of k divided by m, which means that omega squared is equal to k divided by m, so k is equal to omega squared times m. And then we plug in some values, we get that k is equal to 4.33 squared times 0.2, which is equal to 3.75. And that is going to be our value for k that we can plug into our equation. Let's rewrite our equation and solve for g. So mg is equal to negative k times change in y, and you divide both sides by m, and we get that g is equal to negative k times change in y divided by m. And that is equal to negative 3.75 times 31.2 centimeters, which is equal to 0.312 meters, so 0.312 meters, then divided by the mass, which is 0.2, and that is equal to negative 5.85 meters per second. So g on planet X is equal to negative 5.85 meters per second.